Section 2.8 Comparing work for reversible and irreversible processes. We will visualize the work done in the reversible process and irreversible process. Over here, if you look at this curve, this is just PV equals nRT curve for ideal gas. When the system expands reversibly, P external equals P. So you're looking at the expansion here. The red area is the absolute value of the expansion work. And then the system can be compressed back to the initial state reversibly. Again, P external equals P. And in this case, again, the red area is the absolute value of the amount of work. The compression work is equal to the expansion work with opposite signs. What if we do irreversible expansion? In that case, the external pressure will have to be lower than the system pressure. So this area corresponds to the expansion work, and this is negative because the system expands against the surroundings. The system does work to the surroundings. Therefore, this work of the system is negative, this much. When we compress the expanded gas back into its initial state, we need a higher external pressure than the system pressure. So in this case, the larger rectangle, the yellow plus the red, is the compression work. So this P1 is the constant external pressure. Therefore, when we compress this system from V2 back to V1, you need to do this much work, P1 times delta V. So now think about it. The expansion work is P2 times delta V. The compression work is P1 times delta V. So even after the system gets back to the initial state after expansion and compression, although the system gets back to the initial state, there's something that has changed in the surroundings. Why? Because think about it. The system does this much work to the surroundings in its expansion. And the surroundings does more work to the system in the compression. So overall, the surroundings does this much work to the system. The yellow area is the overall amount of work done by the surroundings to the system. Meanwhile, heat flows from the system to the surroundings. How much? Also this much. All right? And then what happens to the surrounding is this. Work is converted to heat for the surroundings. And when work is converted to heat, later you will see that causes the entropy increase of the surroundings. When the entropy of the surroundings increases, while the system gets back to the original state, that means the entropy of the system has no change after the cyclic process. But overall, the entropy of the universe increases, and that's irreversible. So in the real world, it's impossible to achieve a reversible expansion or compression because that requires P external to be equal to P, or the difference between P external and system pressure is infinitesimal. And infinitesimal is impossible to achieve in the real world. But we can somehow get close to this reversible process. For example, when we do expansion, we don't have to do a one-step expansion. We can do two-step expansion. So in this step, this P external is closer to P. Or we can do 5 steps, even 10 steps. When we do 10 steps, you can see the expansion work is the sum of those yellow bars. and that sum is very close to the work done in a reversible process. What's the difference? The difference is the sum of the red regions. But look at the red regions. They get smaller and smaller when we use more and more steps. Now imagine instead of 10 bars, imagine 100 bars. And then in that case, you will see the total area of the 100 yellow bars is going to be very close to the area under this PV equals nRT curve. And in that situation, we say, well, this process is awfully close to a reversible process. When we do compression, we go from higher volume to lower volume. We can do one step compression from here to here with a constant external pressure, but also we can do from here to here. But also we can do two steps. We can first use this external pressure to compress the system, and then we increase the external pressure to here. That's a two-step process. In this two-step irreversible process, you can see the total amount of work is greater than the reversible work. By how much? By this area plus this area. So again, it's just the area of these two green bars minus the area under the PV equals nRT curve. So how can we get this irreversible process to be close to the reversible process? We just do more steps, 5 green bars. Now the area of the 5 green bars is awfully close to the integral under this PV equals nRT curve, or P equals nRT over V curve, the reciprocal curve. What about 10 bars? Again, you look at this area of the 10 bars, it's very close to the integral area under this P equals nRT over V reciprocal curve. Imagine 100 bars. When you have 100 bars, this irreversible 100-step process is awfully close to the reversible process.